Hi guys, welcome to the second part, this recording for the second part of this week. We are in the week before Thanksgiving, so we're still dealing with the stars. We're dealing basically with the life cycle of the stars. So the two remaining units, namely unit 65 and 67, please read the units between because they give you a lot of stories also in between. So 65 and 67, and they deal basically with the end of a star, whether it's a low mass star or also a high mass star. So let me share with you the screen so that we can see the units. So again, in this case, we're dealing with the low mass star. And for the case of the low mass star, it ends in a white dwarf, basically, versus the high mass star, which has two possibilities, is going to end up either as a neutron star or as a black hole. So just a reminder, basically, a low mass star goes through this cycle, basically, where it's in a protostar, where the collisions basically are the ones that are really responsible for heating up the gases trying to coalesce due to the force of gravity. Then it's further compressed rapidly using gravity. This process takes about 1 million years. And then the compression, which is a pre-main sequence, so it's still not a star yet, takes about 20 million years. This is peanuts compared to the age of a star, at least of this size of a low mass. Then it's going to spend most of its life, about 10 billion years, basically, as a main sequence star. For the case of the sun, it's really in the middle of its life here, and it's of this type. It's a low mass star. At some point, then it's going to run out of hydrogen in its core, so it's going to start burning, basically, because it's going to shrink initially, and in doing so, its temperature rises. Remember, we still have helium in the core from the initial helium and the one that is actually produced. So that's going to start to fuse because the temperature rises high enough for it to start to fuse. And the star basically expands so much that it becomes a red giant. After basically it runs out of fuel in its core, this process takes about 1 billion years. So by this time, the sun is already over 10 billion years, 11 billion years at this point. And for the case of the sun, it's going to be so big that its radius grows so much that it's going to engulf in it Mercury, Venus, and Earth, and potentially even all the way to Mars. So it becomes so huge in terms of size that these planets will be populated. They will be pulverized, basically, and we will not be there to witness that. But the point being in here is this is actually the state. Then after it turns out of fuel, it's going to shrink initially, actually, and then it's going to start going through a cycle where it's going to burn hydrogen and helium. And in doing so, actually, it's going to be a variable star of a type Mira. This process takes about 10 million years, and then it's going to expand a nebula at the end because it expands so much that it thins, and the radiation will come out straight out, pushing all of the materials in all directions, namely the carbon and the oxygen that formed and all of the other elements. Basically, they will expand and feed the rest of the interstellar space with these materials. This process takes about 10,000 years, so it's a very, very short process, basically. What is left in here is a white dwarf. And a white dwarf is a very small, basically, it's the core of the star, in this case, the sun, for example, and it's about the size of the Earth, so it's extremely small in size, basically. It shrunk so much compared to its original size that it's 1/100th of its original size in terms of the entire star. When I say original size, when it was in this stage, when it was a main sequence star. So that's basically in a nutshell for the case of a star. In terms of the HR diagram, of course, it migrates as being a protostar. And then because of a force of gravity, it's going to shrink in size, increasing in temperature. So it's going to be more luminous. Temperature rises high enough, at least several million Kelvin, I should say. At that point, nuclear fusion starts in its core. I'm talking the temperature inside the core. I'm not talking the temperature on the surface. Temperature on the surface stays in the thousands of Kelvin, so it's not going to be that hot. But at that point, it's going to be a main sequence star. For the case of the sun, it's midway. It's going to start to increase in size. That's why it's going to migrate even within the main sequence range. and its luminosity starts to increase. For the case of the sun, it's almost 1.5 times more luminous than what it was when it started as a ZAMS. Remember, zero-age main sequence star, so that's the beginning. And it's going to, after that, it's going to go through its red giant state, which takes about 1 billion years, for a total of 11 billion years since it was formed. And then it's going to go to the yellow, so its temperature increases a little, but it shrinks in size at the same time, and then it's going to be a variable of the type Mira. Finally, it's going to shed the nebula. That takes about 10,000 years, and it's going to be a white dwarf. As I said before in the previous session, this is not a real migration of the star. The star does not really migrate in space, but this is just its location, its size, and its basically structure and its temperature change with time. So again, this is the same process described. This is the nebula that forms, the planetary nebula that forms, that is ejected from it. And what is left in here is a fraction of its initial size, which is the white dwarf. When the white dwarf forms, it's extremely hot, usually around 20 to 30,000 Kelvin. And that's because of the shrinking at this point. There is no nuclear reactions happening in it, so it's not feeding more temperature, and it's going to fade over billions of years until its temperature cool enough to become actually a black dwarf. So this is basically, in a nutshell, the process. The planetary nebula, basically the way it forms is, remember, as the star expands, is going to cool, and which allows for the radiation to go straight through, pushing all of the materials that was in the atmosphere of the star, and actually the layers that were in it. That's how the planetary nebula forms. And actually, it's going to be in its wake. So as the star is basically moving, and as it was moving before, so it's going to continue its motion. And the core is really what is left off of the star. And it's really still the main mass of the star. So it's still a big, big mass, albeit it's very, very dense because of the fact that it's very small in size too. So that is going to be left in its wake, and that is the planetary nebula that's going to go and feed the rest of the interstellar space to potentially even be the source for formation of other stars. Again, these are some famous nebulae. This is the Hourglass Nebula. And that is basically also, you have in here, there is a white dwarf, as I was saying. White dwarfs, they have temperature, they're extremely hot initially, and they cool and they become black dwarfs at the end once they run out of energy, and they fade basically too. So again, this is a summary of the entire process. So please go through the reading of this unit for the low mass star, this unit 65. And make sure you go through it. And if you have any questions, please let me know. Let me stop sharing and share the unit dealing with the high mass stars. Again, for the high mass stars, it's a similar process, except the end is far more violent than the case of the small stars, and the process is extremely fast. So again, it starts as a ZAMS, namely the zero-age main sequence star. It goes through a similar process, except with more mass, more temperature, and the process is expedited. Then the star goes through its main sequence life, basically a process that takes about only a few million years, 6.5 million years, compared to billions of years for the case of a low mass star. Now, you have to remember that the reaction inside the high mass star is very, very fast, and it uses, among other things, it's mainly the CNO process, or the CNO cycle, and that is extremely fast. That's why it goes through its materials. It has more materials to begin with, which means that the whole process is expedited. That's why it doesn't live so long. Then it's going to start fusing the hydrogen in its shell when it runs out of the hydrogen in its core, and also starts actually fusing both the hydrogen in its shell and also the helium, and is going to grow in size and become first a blue supergiant, yellow supergiant, red supergiant, and at the end, when it turns out of all of this fuel in its core, is going to basically collapse into a big supernova, an explosion that is going to leave in its wake either a black hole or neutron star. This has high enough temperatures that can generate far, far more elements than a normal low mass star, because it can reach temperatures in the billions of Kelvin, allowing it for it to fuse heavier elements, not just helium, but actually carbon and silicon and oxygen, leading to the formation of iron. Once iron is formed, at that point, there is no way for the star to make up more energy, because iron is a known basically element that is the most stable element. So once it forms it, basically at that point, that's the end of it. There is no more way for it to make more energy to further, if you wish, stop that collapse due to the force of gravity. So there is no more outward pressure to balance the inward gravity, and at that point it's going to collapse drastically. When it does, what is remnant inside basically is going to expel the material that has fallen, and that is going to be the supernova. And the supernova is super hot, actually, that forms even elements, and it would be able to fuse even elements heavier than iron, and that's how most of the periodic table is formed, actually, through this high mass star, more massive stars, and how they go through their process of making materials. Very fast, very violent, but that's basically the difference between it and the low mass star. Again, this is basically the same process explained. Iron is a known, one of the elements in the periodic table that is known. I mean, nuclear actually properties, and I'm not talking about the chemistry, I'm talking about nuclear properties. So iron cannot be basically fused to form more. I mean, it can, but this is not a process that is going to produce energy. You need to supply energy to it for it to happen. And the star really wants energy to prevent itself from falling. So if it cannot fuse it at that point, that's it. It has really, it has reached the end of its life, okay? So again, in terms of temperatures, initially it's fine. I mean, you have the hydrogen fusing, and at low enough temperatures, that is going to be hydrogen either through the CNO process or even the proton-proton chain. Basically, at that point, you're going to produce helium. That is the process. The temperature is about 5,000 Kelvin. That should be enough for it to happen. The star in this case spends only about less than 1% of its mass to convert it into energy. Remember, the energy is produced using this expression. Okay, however mass is converted, that is the energy that is produced, because this c squared is just a number, which is 9 times 10 to the power 16, which is 300 million squared, really, that's all. I'm squaring just this number just to get which is a constant, which is a number. So it's the mass converted into energy. For helium, it needs about 100 million Kelvin. At that point, for the case even of a low mass star, you'll be able to form carbon. So this is a process that is even for a low mass star. This takes about 7 million years for a high mass star. This takes about a tenth of that, 700,000 years. The star basically runs out of helium in its core and starts collapsing, which leads to even higher temperatures, around 200 million Kelvin. This too takes another 700,000 years, which is almost 1 million years, for it to convert the carbon to oxygen by capturing more helium in this case. Now, at this point, once it runs out of this source of energy, it's going to collapse and the temperature increases to about 600 million Kelvin. In which case, the carbon starts to fuse with carbon and forms neon, and plus, of course, helium in this case. And this process is super fast compared to the previous ones. So if this one takes 7 million years, these two processes take almost 1 million years each. This one only 300 years. This is nothing. This is like a blink of an eye in terms of the ages of the stars. So carbon is converted to nitrogen. Once it runs out of that, it's going to collapse further to basically its temperature increases to about 2 billion Kelvin at that point, in which case oxygen starts to fuse to form silicon. Now silicon, again, is a process for the star to maintain itself from further collapse. So at this point, the process takes only about 3 months. So we're talking months now. We're not talking even years. So what took we're not talking 300 years or millions of years or something. We're only a few months. And the star is really toward the end of its life. Once it runs out of that, then it's going to collapse further and its temperature will increase to about 2.5 billion Kelvin. This is high enough for silicon to start to fuse, forming iron. This whole process takes about a day. One day. And then it cannot fuse, no matter how much it collapses, it cannot fuse iron anymore. That's it. So at that point, the collapse will result into a drastic fashion. Look at the process that it's really shell structure that is happening. The hydrogen that was in the core basically made helium, and the helium that was in the core made carbon, and the carbon that was in the core made neon, and the neon that was formed in the core, of course, all of this was in the core, whereas the upper shells, they're started to move up. So you're looking at the shell that is started to grow from inside out, okay? The neon, then the neon, when it's fused, made the oxygen moved out after it basically started to making silicon, and the silicon at the end, when it started forming the iron, moved out. So this is basically the whole shell structure that is happening in the star. Once the iron is formed, at that point, that's it. That's the end. It's only one day, a matter of one day. Then at that point, there is no source of heat to maintain the star from further collapse. So it's going to start collapsing into a ridiculous fashion, where first of all, the electrons are pushed toward the protons. And this is called an electron capture. So a proton plus an electron, this is a normal electron, will form a neutron plus a neutrino. So this is the electron capture. So now what we have made up in this case is neutrons plus neutrinos. Neutrinos, they are ejected immediately. And they take the bulk of the energy from the whole collapse, from the whole process. Neutrons stick with other neutrons and form the core now, the new core of the star. So it's not iron anymore, actually it's neutrons. And the whole thing starts collapsing. And as it collapses, it hits the core and it bounces. The materials that hit the core, they bounce off. When they are bouncing off, they encounter the incoming materials, and the process becomes so hot because of these collisions. This whole thing triggers a tremendous explosion because reaction is happening everywhere, that an explosion goes in all directions. That is the supernova of type 2. This is a type 2 supernova. Okay, the collapse of supermassive stars. And in this case, once those reactions are happening, basically the explosion, the result of which are all the elements in the periodic table, heavier than iron. Everything else is formed during that stage. So that's basically, in a nutshell, how this whole process works. Again, hydrogen and helium were formed during the Big Bang, of course, when the universe formed, and we're going to talk about that down the road. The rest of the elements must have formed in the stars. Up to carbon and oxygen, they can be formed in low-mass stars. But you need supermassive stars to form heavier elements like silicon and all of the other elements that are heavier than up to iron. But then that process is only limited up to iron. Then you need another process, and that is where the supernova comes into play. And that is how basically the rest of the elements in the periodic table are formed. Okay. So all of these elements are fine to be formed up to iron in a normal star. Then after that, the rest of the elements in the periodic table are formed with the collapse of that supermassive star to two scenarios. So initially, yes, it's mainly neutrons that are left, but those neutrons, they can further collapse into a black hole. So this is again a type 2 supernova. Most of the energy is taken by those neutrinos that come from the electron capture. So you have a proton is forced to capture, actually, due to the compression, due to the gravity, to capture an electron. And now the outcome of it is a neutron plus a neutrino. Neutrinos are extremely less massive than anything, and they go straight zooming out of this. So that's what you're going to see first before an actual explosion. If you're monitoring the thing, that is the first outcome. So that is really the first thing that is going to come and tell you, hey, watch out, there is an explosion behind us. So the neutrinos are the messengers of all of these processes. Now, there are different types of supernova. There are two types, really. I mean, more than two. Okay. There is one A supernova, and one A supernova is a white dwarf that forms from a low mass star, having a neighbor, a regular star, and feeding off of it. So basically, it's going to feed off of it, and this forms an accretion disk. So it's going to take more. Remember, white dwarfs are less than the mass of the. It's basically the core of the sun, whatever is left in it. So they're small, relatively speaking. Once that reaches a limit called the Chandrasekhar limit, it's Chandra limit. That's how they call it actually. It's 1.4 the mass of the sun. That is going to explode. Type 1A supernova are important, extremely important, because we know exactly how much mass they require. 1.4 the mass of the sun. So we know exactly how much energy they produce. So they are used, actually, and we'll talk about that down the road, they are used as an important indicator for distances to galaxies. So they are extremely important because we know exactly how much mass they require for them to happen. So this is type 1A. And the other type that we just discussed is the collapse of a supermassive star on its core. And that depends, of course, how big the star is. So the product of that can be different. So it can be bright or less bright or something. It can be even a hypernova. Okay. So this is a type 2. And there are two other basically types, depending on the content in terms of oxygen, whether or not they are deprived of oxygen or not. So they are type 1B and type 1C. Okay. So again, these are some of the processes involved with a supernova. Again, supernova will last only for a few days. I mean, a few days, and then its brightness or luminosity starts to decrease with time. Let me pause to see exactly what happened behind me in here. Hold on, guys. So let me continue with the discussion again. So this process takes only a few days, actually, and then the luminosity will decrease over time. Because again, that whole process of making energy, and then the whole process starts to cool with the expansion of the materials as they are expelled. Here is a supernova remnant. Okay, there is a famous one that happened around the basically 1100, basically about 1,000 years ago. I was going to say 10 centuries ago. So that's basically how this is, and it was documented by the Chinese, Japanese, all countries basically documented it. And it appears as a big, super, basically a bright star that is going to explode. Some of the stars that we're monitoring actually is one of the famous ones is Betelgeuse. Anyway, this is a type 2 supernova, and that's basically how they collapse. And they collapse if they are not too big, then what you have in this case is a neutron star. So that's basically what you end up with. But if they are big enough, even that collapse is not good enough. They are going to collapse further and further into a singularity, and that is what the black hole is. And that came from some bursts in gamma rays, but people, when you look at it, you don't find anything, but you see that for short few seconds, there is a huge gamma ray burst, and those are coming from the hypernovae, and those are the ones that are responsible. They're coming from the collapse of supermassive stars directly into black holes, forming a black hole, not a neutron star. So this is, in a sense, basically how the low mass stars and high mass stars end. And please read the units. If you have any questions, please do not hesitate to ask. Thank you very much. I'm going to stop the recording in here.